Hello students, today I will be teaching you how to verify the theorems of circles of class 10 in an experimental way. So I've got a model made where I've drawn a circles and I put nails around it so that different things, different properties of the circles can be shown, and we will see one by one the theorems. So first of all, start with theorem 1, which says the angle subtended by an arc of a circle at the center is double the angle subtended by it in the remaining part of the circle. So first of all, we need to take an arc. So if I am taking this arc if I am taking, so I have drawn a chord based on that arc, because now the lines, the angles which will be formed will be the angles formed by the lines going from these 2 points, because this is the arc. So if I make an angle which is at the center, I have marked this. So let us measure what this angle is coming as. So if I try to measure this angle, I am getting this angle over here as close to 90 degree. So this is the angle which is formed here is 90 degree. So if I go to mention here that this angle is 90 degree. Now from here only, if I take an angle at the remaining part of the circumference, and go to measure this angle, you can see it is coming here as 45 degree. So if I write here 45 degree, so you can see now, as the theorem says, angle subtended at the center is double the angle subtended at the circumference made by an arc. So this arc is making at the center 90 degree and at the circumference 45 degree, and that will happen in this any part of this remaining part of the circumference. So if I change it to another place and try to measure here also, you can see I will be getting here also coming as 45 degree. Okay, so I go to make this angle anywhere here, then also it will be coming as 45 degree. You can see it is again coming as 45 degree. So I go to make angle anywhere from here to here, everywhere it will be coming 45 degree only. Now even we can try with angle made by this part which will be there, this part of the angle will be coming as 360 minus 90, 270 degree. So this is the major arc making an angle, so remaining part of the circumference is the minor arc. So now if I try to get the angle in the minor arc, now this angle, so let us measure it. Placing it, so you can see here it is going 130, 140, 135. So 135 double is 270. So this angle is coming now as 135 degree. So this verifies this theorem experimentally, how angle at the center is double the angle at the circumference. Now we go to the proving of the next theorem, that is angles in the same segment of a circle are equal. So if I have drawn or marked here, okay, this becomes a chord. So once a chord is there, the circle gets divided into two parts. This is a bigger one, so major segment, this is the segment, and this is the minor smaller part, so this is the minor segment. Theorem says angles in the same segment of a circle are equal. So because of this chord, if I go to make angles anywhere in the major segment, I have got this angle. So let me measure it and see what value it will be coming over here. So it is coming to 45 degree roughly. Now I take another one. So you can see from this 2 point, which are the chords of the circle, angles lines are going one in this part and the other part, both of them are in the major segment. This one we had got it as 45 degree. So if I measure this angle, so here also you can see I am getting it here 40, 50. In between it, so 45 degree. So the angles are coming the same as 45 degree. Okay, now I can change the chord. Okay, now you can see I have changed the chord. Earlier chord was from here to here, now I have changed the chord. So again I am seeing the angles in the major segment only. Okay, so let me see what this angle measurement is coming to. So what I see here, it's coming close to 60 degree. Okay, it is coming close to 60 degree. Now I will just take another one, and again in the major segment I will make one more angle, and let us measure this and see what it is coming to. So you can see here that is also giving me that same 60 degree. So this is 60 degree and this is also 60 degree. So this theorem, angles in the same segment of a circle are equal, gets verified by this. Students, now let us go to verify the next theorem, that is angles in a semicircle is a right angle. So I make a diameter here. So this is the diameter, it separates it into two parts, both are semicircle here. So let me get one angle made here. So this is the angle made in a semicircle. Let us measure this angle and you can see it is coming as 90 degree. Okay, so I go to right here 90 degree. This angle is coming as 90 degree, and semicircle over here is from everywhere over here. So I can take it to the next place and check it there, what angle is coming there. So if I put it properly, so you can see again it is coming as 90 degree. Okay, now another place, if I take it here, still you will get it coming as 90 degree only. Okay, you can see it is coming as 90 degree. So that gives you a very good verification that anywhere you make the angle. So if I go to make it below, in the below semicircle also, you can see if I have tried to make it over here, let us measure it. and you can see here also it is coming as 90 degree. So whether we make it in the upper part of the semicircle or below, everywhere it will be coming as 90 degree. You can see even a quick look also tells you that it is coming as 90 degree here. So that's the way we get a verification that angles in a semicircle will always be 90 degree. So students, I hope you all are enjoying how this verification is taking place by this same one particular apparatus which I have. With this, we are proving all the theorems of circles. So we come to the next theorem, which says the sum of the opposite angles of a cyclic quadrilateral is 180 degree. So you can see I've already placed a rubber band to make a cyclic quadrilateral. A cyclic quadrilateral is the one where all the vertices of the quadrilateral lies on the circumference of the circle. So theorem says the opposite angles, if I take this angle, the opposite one will be here. And if I take this one, opposite one will be here. So let us measure what angle we are getting with this quadrilateral. So what I find here, it is coming as 110 degree over here. This is coming as 110 degree. Now let us see the opposite angle to it. And you can see that it is coming to 70 degree. Okay, so 70 and 110 added gives you 180 degree. Let us see this two pair of opposite angles. This one is giving me very close to, let me adjust it properly, close to 95 degree. Okay, so let me write this one as 95 degree. Now let us measure this. Now when placed properly, you can see it is coming to as 85 degree. Okay, so 95 and 85, if you are adding it up, you are getting it as 180 degrees. So this verifies this theorem. Hope you have liked it and it's making it better for you to understand it. Now let us proceed to the next theorem, which is also based on cyclic quadrilateral. The theorem says that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Now this is the cyclic quadrilateral made. So this side of the quadrilateral has been extended. So this angle becomes the exterior angle. And then beside it is this angle, which is the angle adjacent to it, and opposite to that comes this angle. So according to the theorem, these two angles should be equal. Let us measure and check it. So I am getting this angle coming as 80 degree. Let us measure this angle. And you can see that this angle is also coming as 80 degree. So that's the verification of this theorem, that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Now we move to the theorem which are based on tangent properties. So the next theorem, it says the tangent and radius at the point of contact are perpendicular to each other. So I have already drawn a tangent. Tangent is a line, external line, which touches the circle only at a point. So this is the point at which the tangent is made. Now from this point only, if I go to make a radius, so that is what it says, the tangent and radius at the point of contact. So from this point of contact, if I am making a radius, so this green part is your radius here. Now theorem says when they are perpendicular to each other, means the angle made over here should be 90 degree, and which we can measure and check it. And so you can see, yes, it is coming as 90 degree. So they are perpendicular to each other. So this is 90 degree. So this theorem gets verified here. Students, let us see the next theorem, which is a very lengthy one. It has a lot of 3 parts to it. So the theorem says if 2 tangents are drawn from an external point, so this is the external point I have taken, to a circle, then the first one says the length of the tangents are equal. Second one says the tangents subtend equal angles at the center. This is the center part. The tangents are equally inclined to the line joining the point and the center of the circle. So we'll take it all the 3 of them one by one. We will see to it. So first of all, let us see the first one. This is an external point. So one tangent is drawn here, so which is touching the circle at here. So the length of the tangent will be from this external point up to the point where it is touching the circle, and another one is over here. Okay, so let us measure the length and see it, what it is coming to. So it is coming to nearly 6 centimeter. So this length is 6 centimeter I am getting here. Let us measure this length and see. And that also shows me 6 centimeter. You can see 6 is here, coming to 6 centimeter. So that confirms the first part of it, that the length of the tangents from an external point to a circle are equal. So the first part is verified. Then the second one says the tangent subtends equal angles at the center. So let us get this part drawn. So I have joined the center with the point of contact where the tangent is touching the circle. The next one also done. Now I will be joining the center with the point from where the tangents are drawn. So theorem, what it says now, the second part, the tangent, this is the tangent, they subtend equal angle at the center. So this tangent will be subtending this angle, and this is the next tangent. At the center it will be subtending this angle. Let us measure and see what are their values coming to. So what I get to see here, it is coming as 30 degree, this angle, and then I measure the next one. You can see it is also coming as 30 degree over here. So here I have got them coming as 30 degree, both of them. So the tangents are subtending equal angles at the center. That's the proof of the second part. The third part says the tangents are equally inclined to the line joining the point and the center of the circle. So these are the 2 tangents. This is the center and this is the point from where the tangent is drawn. Equally inclined means it is the angle which the tangent is making with the line which is joining the center and the point. So we have to take a look at the measurement of these 2. So let us measure and see what we are getting here. So you can see here we are getting it as close to 60 degree, and let us measure this and see. So we are getting it as 60 degree. Exact it will not be coming because you can see the lines using a rubber band is not coming perfectly straight. So here I am getting here 60 degree, and here also I am getting a 60 degree. So all the 3 parts over here, that is the length of the tangents are equal, verified. the angle made by the tangent at the center equal here, and the tangents are equally inclined to the line joining the center has been verified. We move to the next theorem. It says if two chords of a circle intersect internally or externally, then the products of the lengths of the segments are equal. So I have drawn one chord. Let me put another chord. So the two chords are cutting each other at this point. Now here the segment is not the segment of a circle but the line segment of the chord. So the two chords are intersecting over here. The theorem says that the product of this part into this part should come equal to the product of this part into this part. So let us measure it and see what we get it. So I am first of all measuring here. What I get here, it is coming at nearly 7 over here, and here it is coming to 16.6. So it means that this is 7 and till here it is 16.6. So it will be coming here as 9.6. So if I write that value here, this is 7 centimeter and this is 9.6. If we multiply these two, 7 into 9.6, we get it here as 67.2 centimeter. Let us measure the next part. I will just measure it from this part so that it will be looking better. So what I find, from here to here it is coming nearly at 5, and then here it is coming to 18.5. So from here to here is 5, then this becomes 13.5. So if I write here this one as 5 and this one as 13.5 and multiply this, 5 into 13.5 will give me here 67.5. So with an experimental error, you can see the product of the two segments here giving me 67.2 and here giving me 67.5. So nearly they have come as equal. Okay, so that verifies that when they are meeting it, intersecting it internally, the product of the line segments which are formed of the two of the parts from the chords are equal. They are getting it as equal. We had seen about the internal intersection. Now we will see external intersection. There are two chords. This is one chord extended to meet at the external point, and this is another chord meeting at the external point here. So this is the meeting point externally. So we need to take the measurement for this part of the segment and this complete part of the segment, and then this part of the segment to this complete part of the segment, and then see what their products of the lengths is giving us. So let us measure this. So the measurement on putting the scale, this from here till here, it is coming as 4, and from here till here it is coming as 20. So if I write this measurement here as 4, and this 20 is the entire length which is there, 20. So 4 into 20 gives me 80 centimeter square. Now let us take the other chord, the two line segment, what we are getting here. Remember that the meeting point is where it is touching the circle, not this nail, but at this point. So what I get to see here is that the measurement is, on keeping here properly, 5.2 it is here, and here it is coming as 15.5. So 5.2 and 15.5 for this entire length. So if I multiply here 5.2 into 15.5, I get it as 80.6. So with an experimental error of 0.6, we are getting it as nearly as same. So for externally intersection also, the products of the line lengths of the two segments are equal. So this is also verified. Now we proceed to theorem number 9, which is also called as alternate segment theorem. The theorem says the angle made by the tangent and the chord at the point of contact is equal to the angle made by the chord in the alternate segment of the circle. So currently here you can see this one is the tangent, this is the point of contact where the tangent is meeting the touching the circle, and this is the chord drawn at the point of contact. Now there are two angles made by the tangent and the chord. This is one angle. If I am taking this angle made by the chord and the tangent, then this segment of the circle is called as the same segment, and this part, entire this part, becomes the alternate segment. So theorem says whatever the angle will be made by the tangent at the chord here in this segment, then the alternate segment is this. Wherever this chord makes angle in this alternate segment, this angle will be equal to that angle. Let us check it out. So I have made that angle here. So let us measure this angle first. So it is coming very close to 45 degree. I will be writing here as 45 degree. Then this chord is making this angle in the alternate segment. So let us measure this angle. Keeping it properly, so you can see it is coming at 45 degree over here. So that confirms that angles made by the tangent and the chord is equal to the angle made by the chord in the alternate segment. We can check it at one more place. So if I just change it to another place and see here, measure this angle, and you get to notice here that it is going at 45 degree. So this angle also formed here is 45 degrees. So that confirms and verifies this theorem, which is alternate segment theorem.